So thank you. Thank you for this invitation in this very special place. And I'm very glad, also very grateful to the Pontifical Academy for intermixing topics that are usually not part of scientific conferences. It's so important. And I've been looking forward to a conference like this for many, many years. So thank you for bringing us all in all topics, not dividing topics on outreach is one thing and science is another and society is another. So in this talk, I will tell a short story. I apologize, I'll have to skip on many details, but I'll try to tell the broad story, but a very exciting one. Exciting not only for its implications for planet formation, but also because I think, as you'll see, that it tells an example of how research happens, how the adventure of research happens for us researchers, where hypotheses are proposed, and then maybe for decades we have to wait for a confirmation, and in the meantime there are hints of a discovery and failures and frustration and persistency, and then at the end a surprise. So I think this is one example of what often happens in science. And this work is based on a program I proposed for Cycle 1, a GEO program, but it delivers work from a broader collaboration called JDiscs, that is a free union of PIs from GEO programs in Cycle 1, of which many are here, Klaus, Colette, and Karen. So to fully appreciate what JWST has shown us in this context, I like to go back to the solar system studies. This is a beautiful, simple cartoon from 1998 that shows all the ingredients of the story, and some have already been introduced by Colette. The solar nebula, this is a section of the solar nebula, the protoplanetary disk of gas and dust where our solar system was formed, so the sun at the center. And these studies were trying to explain observations of the solar system and its formation and some properties that were observed. So we have already seen that there is this global temperature gradient. The nebula or protoplanetary disks are hotter, closer to the sun or stars, and they become progressively colder going out. The snow line, it's a region that separates these two global regions, one when there is water vapor closer in the warmer regions, and the other outer where there is ice. This snow line has been proposed for a long time as a key place for planet formation, for speeding up planet formation. In this work in particular, I like these the two words up there, ice drift. So this process was proposed back then to explain the rapid formation of Jupiter's core, bringing in solids rapidly enough to build Jupiter's core, but also to explain chemical gradients and evidence for radial mixing across the snow line. So a fundamental process, ice drift and mixing of water and ice across the snow line between the ice and the vapor. So fast forward, this process of pebble drift has become a key element of planet formation theories. So this is a recent example from Lambrecht et al., where you can see from the plot to the left and the cartoons to the right, this is essentially a solid mass delivery issue. So if a disk is delivering a larger mass of solids to inside the snow line, a system of super Earths depicted in the artist illustration at the top may form. Instead, if the disk for some reason delivers less mass in pebbles to the inner disk, the growth of planets is limited to small rocky planets. But what are these pebbles? Let's say a few words about those. These are aerodynamically marginally decoupled solids. So they are not too small to the very left that they follow completely the motion of the gas, and they are not too large to be essentially independent. They live in that region in between these two extremes where they feel a gas drag that brings them close to the star and even onto the star. So this size, the favorite size of this gas drag, it depends on the gas density. So it's essentially millimeter-sized grains in the outer disk, but it's meter-sized objects at 1 AU in the location of Earth. So this was the origin of this posed a very serious problem in planet formation theories that came to be known as the meter-sized barrier. In this plot here, you see that the particle of 1 meter size would drift in about 100 years on the star. So this was a huge problem, huge implication that there should be no disk and no planet, and yet there are. So this is a fundamental physical problem that was very hard to get rid of, unless, and some years later, people proposed that there might be overdensities in pressure that would provide effective pebble traps, trapping these solids at specific locations. And there was a very visionary simulation that was produced in 2012 by Paola Pinilla et al. You see it at the sort of the center in the bottom right. That simulation with many rings, that's a simulation where they said, if this is happening, if pebble drift, if there are pebble traps in the disk and they are really trapped in the outer disk, this is what we should see. And just to tell you how visionary that was, you can compare to the left where you see the vision we had of disks at that time. They look just like a big blob of stuff. Until ALMA came online, stunning the world with these beautiful images of very sharp rings in disks, right? So demonstrating that that prediction was correct 3 years later. So the prediction came in 2012. So what a joy for the group. I always wonder, looking back at that, think of Paola Pinilla and all the collaborators, what a joy to see after 3 years then. But ALMA showed us another thing, that not all disks have rings. Some are extremely small, as you see in the bottom of that figure. And this is a very active field of research now, but the picture that is coming out in the context of pebble drift is that you see I labeled A and B. So the A disks, the small disks, are drift dominated. They have sent a lot of ice solid mass to the inner disk. And the B disk, labeled B, are those that have retained a lot of solid mass in the outer disk. So let's leave this and move to water, the other big ingredient in the story, with another exceptional discovery from the Spitzer Space Telescope. And here we have some of the pioneers, Klaus Pontoppidan and Colette Stalik, a beautiful dense forest of these lines of water, showing us that we could, for the first time, study water at 1 AU, the distance of Earth from the sun. So immediately, it was the hope to be able to tell the story of water as it comes from regions of supply formation to Earth. And there was another visionary plot that Klaus made at the time, showing us what we were missing. So Spitzer was not really meant to do this. And so what he was showing us was subsampled blends of many lines of water that you see on the plot of the right, with a high resolving power at the top and the resolving power of Spitzer, lower resolving power at the bottom. So this is essentially what we have seen yesterday about images, now having a sharper image. When you've seen a comparison between HST and JWST, it's the same effect that happens spectrally. So essentially, Spitzer was delivering us a very blurred vision of water and disks. And what are the consequences? That I was a young PhD student. I started my PhD when this discovery just happened. So my advisor was very excited. He sent me immediately to search for confirmation of this ice migration process, learning from the solar system studies, looked for a confirmation in protoplanetary disks, and it failed. It gave inconclusive results. This was a lot of work for a PhD student and a lot of frustration also. Imagine, I never saw this paper published. It's only my PhD thesis, and I know that some of you have examples of papers that where you put a lot of work and was valuable work and was never published. But persistence here comes into the story. 10 years later, about 10 years later, we could set up a better experiment where we're still using Spitzer spectra with their problems. Now we had the high resolution ALMA images showing us small disks, compact disks, where it was proposed that they should be drift dominated, so sending a lot of ice in the inner region, and the large disk with gaps and rings that are proposed to retain that mass in the outer disk. And at the center top, you see models by Kalyan et al., who worked with me over the past 3 years, proposing how that effect should have been visible. So a difference in ice delivery to the inner disk should have been visible in a different enrichment of water vapor. And here is where JWST comes into play, because we should have seen this higher mass of water vapor in the inner disk at the top of that figure, at the top of the bell. That's the maximum enrichment that with a lot of ice coming in, you should see in vapor. And yes, finally in 2020, we saw a signal in the form of a trend between the water luminosity and the size of the disk, and the interpretation is to the center there. So essentially, in the compact disk, we saw stronger water, and in the large disk with multiple gaps, we see weaker water. Yet, our interpretation was still extremely limited. Once again, we were limited by the resolution of Spitzer because, again, we couldn't deblend these lines and understand better the properties of water. So once again, the resolving power, the quality of the data was limiting us. And here is where the hero comes into the story, JWST, with a 7 times larger mirror and 5 times better resolving power. In 2023, just before we received any spectra from JWST, we published the largest survey combining 4 different instruments of water vapor, also spectrally resolved from the ground. So the state of the art of what could be done before JWST. And we included at the end of the paper a prediction of what we should have seen with JWST. It was nothing special, it's just a simulation. But it's already stunning enough to see the quality of improvement that we should have seen from Spitzer at the bottom to JWST. This much sharper view of lines. And I added a note there. You can play now yourself with the data and with these molecular simulations with a fantastic interactive tool that 2 of my students at Texas State made and that it's available on GitHub. So the data came in, and it was really stunning after a few months. Now we published that paper, and the data came in, were stunning. This beautiful molecular forest, about 1,000 lines there that we can count. And at that time, even though we were all ready, and I remember actually in 1 week, I got the result that eventually came out in the paper. But at the beginning, the result was very unclear. I was finding that the compact disks at the top in black looked overall colder, their water. It didn't seem to be more, it seemed to be colder. And the water in the large disk that should have retained ice in the outer disk looked overall hotter. And this is the lesson that he taught me, because I realized that even the best data are not enough if there is not the right question, if you're not asking the right question. Or in other words, the right question is what makes the difference. The right question is what allows you to see something that is right there, but you could not see before, simply because you were not paying attention. And I learned that from an Italian chocolate maker. I don't know what they do in their factory, but I think these words describe so perfectly what happens to us in research as scientists, so many times. So in this case, the right question to ask was to look back at something that was mentioned already earlier, that water, as many other molecules, essentially give us astronomers a thermometer in space. So if you look at the relative excitation of water lines from different energy levels, you can sort of measure the temperature of that region in space. But in particular for this work, if we wanted to test a process that was happening at the ice sublimation front, we should focus on the low energy lines tracing the colder water. And as soon as we sharpened the question, the answer came out very strongly. So these are the two pairs of disks. So the large disks are in gray, the compact disks are in black. And in the figure, you see their spectra, portions of their spectra overlapped. And you see that their high energy lines are perfectly matching. But there is always an excess in the low energy lines, in the cold water. You take a difference of the spectra, you fit it, and you get a temperature that is right there, very close to the sublimation temperature, the snowline region. So looking back at Spitzer, we could have never seen that effect. That's why we didn't. So what are we learning? This is the interpretation we are giving to this signal, to this cold water excess that we see in the compact disks at the top left, where we think we see this wave of ice solids coming in, being sublimating, diffusing upward, heating up, and rediffusing out. And this cycle of water is stronger in the compact disk because there is more ice coming in, and it's reduced in the large disk because of these retaining pebbles in ring. Now, this is to reiterate on the importance of public outreach and having different skills. Public outreach departments do a much better job in communicating to the people. This is the press release from SDSCI presenting this work and this discovery to the public. Just last week, there was a new version published on Scientific American, these beautiful cartoons. Unfortunately, I love spectroscopy, but it's true. Spectroscopy needs to be told to people in a way that understood, right? And so we have to picture these cartoons using our imaginations to show what we are learning. And then just 10 seconds each. What's coming up next? Carlos Munoz Romero, a student at Harvard with Karen, now is extracting estimates of the solid ice mass that is delivered to the rocky planet region from this data. These are clearly initial estimates. They will evolve in the future for sure, but the exciting thing is that we are at the time of being able to extract these estimates, how much solid mass is being delivered to the rocky planet region. At least in orders of magnitude, it seems that there is a factor of 10 difference between the compact disk and the large disk. So this would have a huge impact on the type of planets that can form in the rocky planet region. And second and last, Anusha and Whitney have been working on a series of papers investigating from the modeling point of view how different planets, and I heard the question coming up earlier, so Neptune would produce only a leaky gap, so pebbles would still flow in through that gap and still enrich the inner disk with ice and vapor. And they've been simulating different types of planetary systems and exploring which ones with how the delivery of water to the inner disk would be reduced in different situations. And yeah, and I'll stop here with this final reflection, these beautiful words that we have been addressed at this workshop that I found particularly really, really beautiful. My hope is that you will not remain content with the results of your research until you have also had the experience of being surprised.